Right, gentlemen, stepper motors. They are, as the name sort of suggests, they are a motor that moves one step at a time. So they turn in incremental steps. Sort of a digital version of an electric motor. Each step being defined by a step angle. What we're going to do on the board is look at it in terms of one that's got quite a coarse step. Real ones that are used in industry have got quite fine steps to them, so they can move, and you wouldn't notice in normal operation that they were moving in steps because they're moving so fast anyway. Okay, so we think we got a start position and we move around one step angle and then a second step angle and so on. Okay. Why a stepper motor? So, some advantages. They are relatively inexpensive. Ideal for open loop positional control. Are you aware of what we mean by open loop? If you go on. No feedback. Yeah, so you can do positioning applications where you want to move. So if you've got, let's say we had a conveyor, fair, yeah, and we wanted to move a small box from position X to position Y, and we wanted that to move exactly 1,000 millimeters. We want it to be precise about moving that from there to there. A stepper motor will allow us to do that without having some kind of sensor that will count how far the belt has moved or measure how far the belt has moved. And I'm not talking about having an optical sensor, a digital sensor there. I'm talking about having a sensor that will know where this is at any position. It will know when it's 501 millimeters along there. That would be having feedback. A stepper motor can do it without that, because what you can do is know the number of pulses it takes, the number of steps it takes to move that block from there to there, without having any kind of sensor on the conveyor or on the motor. You just say, please move 1,000 steps, if one step is a millimeter. All right, Luke? Yeah? So it doesn't have to have any, it can be implemented with feedback. There is a proviso on that, and we'll go through that shortly when we talk about in detail about the control, but it can be done. Okay? So therefore it minimises the sensing devices. We just count the number of steps we want and move that number of steps, and if you're doing it right, you'll get accurate movement. There are some provisos we'll come back to later. Also with torque, stepper motors, and you'll see why shortly, will hold their position firmly when they aren't turning. Okay, so you can make it so they're effectively braked when they're in a stationary position, eliminating the need for mechanical brakes, and they produce better torque than DC motors at lower speeds. Okay, so there's some of the advantages of stepper motors. Right? Everything okay so far? You're all with me? So, main components. A simple stepper motor will have a stator with a number of windings. So we've got some windings or phases here, that if we energise these, we'd create poles north and south on the ends of these magnets here. Yeah, so like a normal motor would have, you've got coils creating a stator field. All right. A rotor, which can be magnetised, so it can be a permanent magnet, or it can be just an iron, non-permanent, okay, depending on the type of stepper motor. We're going to look at some of the different types a bit later on. So that the rotor, the bit that turns, can either be a permanent magnet or a non-permanent magnet, dependent upon type. If we look at this diagram, we apply a voltage to the winding and initiate current flow, we get some magnetic flux between the north and south poles. So we get a directional flux from this north pole to the south pole of the rotor, through the rotor, north pole, ultimately wanting to go from there to there. And that flux will want to take the easiest path. And the easiest path would happen if this south pole will attract to that north pole. It wants to go straight, and so it has the effect of turning that south-north pole rotor in that direction until it aligns with the poles that are created by the energized coil. So it steps round. Yeah. So that rotor rotates to minimize the flux path or reluctance. It wants to create the shortest path for the field to take, and it would rather go through the magnetic material than it would be go around it, and so it has that effect of trying to straighten the path out as much as possible. And reluctance is the magnetic equivalent of resistance. So if you reduce the reluctance, you get more field. All right? Effectively. So, there are three general types of stepper motor. Permanent magnet, they have got a magnetic rotor. Variable reluctance, they've got a non-magnetic geared rotor. We'll look at the detail of that shortly. And then hybrid, which combines the characteristics from the permanent magnet and the variable reluctance, and so it's got a magnetic geared rotor. Yeah, so it combines the two. Like anything else, they come up with some idea, and then over the years they develop it so they get hybrids of it and such like for particular applications. So, magnetic rotor, magnet motor. If we increase the pole pairs in the rotor, we're going to change the step angle. We're going to have more steps per revolution. Okay? Because if we, in the current position, if we magnetise coil B so that this becomes a north and that end becomes a south, we're going to get it to move that distance from there to there. Yeah. So we're creating a smaller step angle by putting more pole pairs in the rotor. Alternatively, we can increase the number of phases we have electrically, so the number of energized coils that we put around the rotor will also change the step angle, because the idea is that we energize these coils in order. We're going to come on to a little bit. So if we go A, B, C, D, reversed A, reverse B, reverse C, reverse D, that motor is eventually going to go all the way round. And it's going to go round one step at a time. Yeah. So the more coils we put on, bearing in mind there's always some kind of mechanical limit to how many you can fit in. But the more we have, the smaller overall step angle we get for each step in the sequence. Any questions so far? So what we do, as I've sort of already half described, we rotate by energizing each winding in turn. So as you can see, we've got current flowing in one coil B through B dash. We get a north-south pole on the B winding, and the rotor aligns with that. Yeah. So we've moved from there to there, let's say. Okay. Next step in the sequence. That go then or not? Yeah, it did. Is to energize coil A through A dash into A, moves from there to there. Yeah. Let's go on quick. You get the point though. That's how it steps round, and we look in a little bit more detail at coil sequencing later, because we'll look at how you can do full step and half step methods, so you can actually do half of the natural angle each step by switching the coils in different ways. Right? Second type, variable reluctance. So it's a non-magnetic rotor made of soft iron, laminated, or it's got teeth on it that align, as we switch them, that align with the coils. Greater resolution, so smaller stepping angles are achieved by putting more teeth on the rotor. Yeah. And there's always at least one more tooth than there is coils around the stator. So if you look at that, we've got 3 coils, A, B and C, but we've got 4 steps or teeth on the rotor. And the reason for that will become clear shortly. Normally you have 3 or 5 stator windings and energize those one at a time. So in this particular case, we've energized A so that we've got a north pole at the top, south pole at the bottom. We'll get a flux through the iron core so that it aligns with those 2 poles. If we then energize C so that we get a north was effectively moved from there to there. So we turned A off and turned C on. If we turned A off and turned B on, what would happen? Go the opposite way. So we just changed the direction by changing the order of the sequence. Yep. I do apologise, but I don't have permission to do colour printing, unfortunately. So your notes are in black and white. But this file will be made available to you. So if you want a coloured version, you can print one off or look at it on your computers. All right? And then energising coil B has moved us from there to there. The next move would be to energise A, but in the opposite direction to what we did when A was first energised, so that we end up with a north pole this end and a south pole at the top to carry the motor on going round in this direction. All right? So if we keep stepping, energising those coils in a sequence, we're going to go all the way round, and then if we keep pulsing, we're going to keep going round and round. We've got a motor action. Albeit in our example one on the board, quite big steps. It'll be quite a jerky motion, but a real one has much smaller steps than that. Alright. Next slide, I'm not too sure why that one's in there, to be honest with you. I'm going to worry about that for now. Hybrid. Hybrid permanent magnet and variable reluctance type motors. They have a stator with windings in them, okay, and then they have a rotor that's got a south cup and a north cup, and that's a permanent magnet, but it's got like teeth on it like the reluctance motor. And I've used colour here again to show that the teeth are out of step with each other on the two halves of the rotor. If you look at side-on view. So as it goes in, the teeth that are on the outside are out of step with each other. They're not in line with each other. If we're now we're looking end on, and we can see we're looking at the red end, but we can see the little green bits of the south pole also showing through because they're not in line with each other. Yeah. We'll energise the coils so that we create double north poles and double south poles and create alignments with the two halves of the rotor. I have to admit I found this quite difficult to pick up first time through. What should be graphic from that is, remember I said about no need for brake. If you leave a coil energized when you want to stop it, you've got that hold and torque on that motor, and that's what that was talking about. Yeah, so that's that advantage. If you want it to stop and hold that position so it don't move, you can do that easily with a stepper motor. This really isn't very clear. Hang on, just look at the detail, these little detailed ones at the top here. See if I can make them, just pause. Now I've zoomed it in, you can see that the poles have got teeth on them. Yeah? So we've got we've got two norths, and because the poles have got teeth on them as well, here, these little teeth, they're aligning with the green south teeth on the rotor. Yeah, there and there. The south ones are aligning with the red. Yeah. And then when we move onto the next slide, and we've moved that around a little bit, because we've changed the position of the norths, we'd have gone round one of those small steps. So just by having them out of line, we've made our step smaller. We've got the advantage of the reluctance motor of it making it easier to have. Because remember what with the permanent magnet, we either had to have more poles in the rotor or have more coils around the outside. But here, because of that small step between the two outer line parts of the rotor, we've got a much smaller step with the permanent magnet rotor, and that has some advantages, some disadvantages, which we'll talk about shortly. Yeah. This slide is an attempt, and I need to zoom it back out again now. There's an attempt to show 4 steps, 4 different steps. We're energizing I in that direction. As soon as I draw a circle, it does that. I in that direction, B in that direction. Then we energize they're both in the opposite direction, then one in one direction, one in the other. Oh, sorry, from that one, we keep B the same, but reverse A. Then we reverse B, and then we reverse A back, and the next step would be to go back to that one. So that's the sequence, and each one of those steps moves that motor around one tooth. Yeah. So to get a smaller resolution of movement, we just mill extra teeth on the rotor. Yeah. Which is what's done with the variable reluctance as well, but there's a disadvantage to the variable reluctance that again we'll talk about or we'll go through in a minute. Right? And that I believe is on this slide here. So permanent magnet versus variable reluctance versus hybrid. Well, on cost, permanent magnet is easily the cheapest. Variable reluctance is moderate. Hybrid is the most expensive, and that's due to the manufacturing process for the rotor is higher. There's more to do. Design, the permanent magnet is moderately complex because of trying to get the number of coils around it that you need to get the step size. Variable reluctance is simple. Hybrid is complex because of the north and south pole of the rotor, and it's complex in terms of the machining that needs to be done to make that. The resolution, the step size for a permanent magnet can be steps between 30 degrees and 3 degrees as achievable. We can get down to 1.8 degree steps and possibly even smaller with the VR and the hybrid types. So there's the big advantage, smaller step sizes. Torque versus speed. Less pronounced torque drop at higher speeds for your variable reluctance motor. The other two boxes being blank, I can only suggest that there's very little difference to them. The middle one is an advantage of the variable reluctance motor. Okay. Noise. Permanent magnet motors are quiet. Hybrid motors are quiet. Variable reluctance motors are noisy no matter what type of excitation, method of energizing them is used. So I should imagine that the variable reluctance was developed because of creating the smaller step angles, found to be noisy, and then someone come up with a hybrid. I can only imagine that's what happened, okay? But that's something that you, if you're interested in the subject or needed to know, you might actually go out and research a little deeper. As far as the stepping of them goes, you can do full half and micro stepping with magnet type, permanent magnet type. You can do full half and micro stepping with the hybrid, but the variable reluctance typically runs in full step mode only. So you can only go one complete step of the rotor at a time. We can make that variable amounts of degrees just by putting more steps on the rotor. Alright, so that's some idea of some of the advantages and the disadvantages of the different types of stepper motor.